In the previous lesson, we were looking at converting energy between two different things. In general, we were looking at converting between kinetic energy and gravitational potential energy, or from gravitational potential energy to kinetic energy. And when we were looking at those problems, we were considering it a closed system, meaning that all of the energy that was gravitational potential energy was converted into kinetic energy, and that no energy was lost in any other way or transformed into any other form of energy, okay? But energy transfer is not 100% efficient. There's friction between objects and mechanical parts, which causes thermal energy to be released, and it reduces the amount of energy that is transferred into like kinetic energy, for example. Okay, so consider the conventional incandescent light bulb, which they don't really make many of them now, and you'll see why. It's because they're very inefficient. Only 5% of the energy input is used to create the light. 95% of the energy input is converted into thermal energy, which does not contribute to the light bulb as a source of light. It's actually much more efficient as being a heater, okay? Because with the incandescent light bulbs, basically what it did was it would shoot electricity through it, and the energy would heat up the filament until the filament got hot enough in order to start glowing, okay? So it was actually more efficient at being a heater than it was producing light, okay? So for our efficiency equation, we have efficiency equals the E out divided by the E in times 100%. So E out is the useful energy, or the output, and E in is the total energy that was input to the system. So efficiency is a unitless percent, and it must be less than 100%. Okay, if you put in a certain amount of energy, you're not going to get out more energy in this case. Okay, it's generally going to be less. So since no energy transformation is 100% efficient, the E out is always going to be less than the E in. So when determining the E out, consider how much work was done to the object and the useful transfer of energy. So when determining E in, consider how much energy was actually used to perform the task. And this sometimes requires a calculation involving power. So for this first example, it says, what is the efficiency of a crane that uses 5.1 times 10 to the 5th joules of energy to lift 1,000 kilograms, a vertical height of 32.0 meters, okay? So if it's using the 5.1 times 10 to the 5th power joules, that's the energy in. Is equal to our 5.1 times 10 to the 5th joules. Okay. And it wants to know what's the efficiency if it lifts 100 kilograms, a vertical height of 32.0 meters. Okay, so if we had our mass or lift, that is 1,000 kilograms, okay, the crane is applying work in the upward direction, okay, and we are just going to assume that it's at a constant speed, so we can find f of g to be equal of f of a. So remember, to find f of g, we're just going to take the mass, so 1,000 times our constant 9.8. So our f of g is going to be 9,800, and so our f of a is going to be the same, just in the opposite direction. Okay, so our energy out is going to be equal to the work being done. Okay, so remember, work is our f of a delta d cosine of theta, where theta is the direction of displacement. Our direction of displacement is this way. It's going upwards. Okay, so our F of A is working in the same direction. So our angle of theta will be 0. So our E out is equal to our FA, which is 9,800 times the displacement, which they gave us in the problem, is 32 meters times cosine of 0 degrees. And we'll find that our energy output is 313,600 joules. Okay, but they didn't ask us for the energy output, it asked us for the efficiency. So for the efficiency, we're going to take the E out, which we just calculated, divide it by the E in, which they gave us as 5.1 times 10 to the 5th power, joules, times 100%. Okay, and I'll go ahead and show you this on a calculator. So we have 313,600 divided by 5.1 times 10, and you can hit the EE button to the 5th power, okay, and then times 100, and I get 61.5%. Efficient. So for example 2, what is the useful energy output when a 60-watt light bulb is on for 2 hours? Okay, recall that traditional light bulbs are only 5% efficient. Okay, so they did give us something in watts. Okay, remember watts is our power unit. Okay, they also gave us a time. So if you remember, power is equal to change in energy or work over change in time. And so if we rearrange this so that it's telling us the amount of energy put in, we would multiply both sides by time. So we would get that the energy in is equal to power times the time. Okay, so for our time unit, they did give it to us in hours. We do need to convert that into seconds. So in 1 hour, there are 3,600 seconds. So our time is 7,200 seconds. And they already told us what the power was. It was 60. So when we go in to plug into this equation, our power was 60 times our 7,200. And we'll get that the energy input was 432,000. Okay. They also told us the efficiency was 5%. Okay, so if we know that the equation for efficiency is equal to E out over E in times 100%, we can rearrange this equation to solve for E out. Okay, so first I'm going to divide by 100. Okay, so then I'll have my efficiency, which actually I'm just going to fill in the number. They told us that the efficiency was 5%. Okay, I'm going to divide both sides by 100, so divide by 100%. Okay, and then to get the E in over on the other side, I'm going to multiply both sides by E in, so times E in will give me E out. Okay, so the energy in we just calculated here. So we're going to plug that into our equation. So my 5 divided by 100% will give me 0.05 times my energy in, 432,000. And I'll get that my E out is 21,600 joules. So a fluorescent tube has a power rating of 32 watts. Okay, so this is our power. It is also left on for 2 hours. Okay, and we just converted that. We know that the time for 2 hours is 7,200 seconds. Okay, and 92,160 joules of energy was used to produce radiant energy. What is the efficiency of the fluorescent tube? So they told us the amount that was just used for radiant energy. So this number here is our E out. We need to figure out how much was put in. Okay, so for our E in, just like before, we're going to take power times our change in time. So 32 times our 7,200. And we'll get that the E in is equal to 230,400 joules. Okay, so now we need to find the efficiency. So efficiency, as a reminder, is E out over E in times 100%. So our E out was given to us as 92,160 joules over our E in, which we calculated, times by 100, and we'll get that our efficiency is 40%. Question 1 is pretty straightforward. You're just finding the efficiency, and they give you the energy in and the energy out in the problem. For the second one, they are asking you to find energy in. So it's going to be similar to the second problem, or no. It is going to be similar to the second problem that we did, in that you're going to have to rearrange. So you won't rearrange it into this one because we're trying to solve for E in instead of E out. But you will be rearranging the equation like we did similarly in example number 2. And then question number 3 is very similar to the practice problem, the very first practice problem that we did. We are going to have to calculate the energy out by calculating work being done. So the FA times delta D cosine of theta. So it would probably help to draw a free body diagram on this just to make sure that you understand the directions that you're going to be using. And so you'll find the energy out, and then you'll utilize that to find the efficiency of the crane.